And there you go. So if you have bounds, you just go back and use the fundamental theorem of calculus. I mean, there is an integration by parts you could write with bounds. If you write it with bounds, it looks like this. A to B. You evaluate the UV from A to B. And this goes from A to B. So like you can do integration by parts with the bounds on it if you want. It just seems simpler to me to do it, figure out the integration by parts, and then go use the fundamental theorem of calculus separately. I mean, that just, you're less prone to make a mistake. If you do this, you're trying to do everything at once. It just seems more error prone to me to do it that way. So I'll mention it, but I'm not going to do it. One last problem before the break. What? Nothing? You know I'm very easily distracted. I should have warned you. What if we have x squared e to the x dx? So what we're going to do here is we'll make this the dv, and we'll make this the u. All right? So u equal x squared dv e to the x dx. So we get du is 2x dx dv. V is equal to e to the x again. Easy question? Okay. Easy, no question. X squared e to the x. Oh, I'm sorry, I should write. So uv minus integral of v du, which is what? X squared e to the x minus the integral of e to the x times 2x dx. Oh, man. Well, this one's require a little bit more patience. Well, this is nice. I mean, at least we've gone from having x squared to now just having an x, right? Let me just write one more step here. It says x squared e to the x minus the integral of 2x e to the x dx. All right. So it looks like we're going to make a second integration by parts. All right. Now the second integration by parts we're going to make here, in order to not make it, let's not be, let me use some different language. So let me call this dv2, and I'll call this u2, right? So like u2 equal to 2x, dv2 equal to e to the x dx. With that choice, we've got du2 is equal to 2 dx, and we've got v2 is e to the x. Does that make sense, what I'm doing? I mean, let's see in the next step if we can follow me. So what we got is x squared e to the x minus, and then I'm going to put some big parentheses around what we're doing, all right? So big parentheses, and what goes inside the parentheses is u2 v2 minus the integral of v2 du2. Which is what? Let's see here. So we've got x squared e to the x minus big parentheses u2 v2, which is 2x e to the x minus the integral v2, which was e to the x, du2, which was 2 dx. Sorry, it should have been blue. All right, it's bothering me. I'm going to fix it. There, it's better. All right. And then, hey, this is the integral of 2 times e to the x. That's just 2e to the x, right? So we're done. So we get x squared e to the x minus 2x e to the x minus minus gives me plus 2e to the x plus a constant. And there you have it. Mm-hmm. It's from the DU2. The DU2 is. No? There is an easier way to do these problems, by the way. This particular one, the easiest way to do is just to guess that the solution has the form ax squared plus bx plus c times e to the x, and just differentiate this and set it equal to x squared e to the x. That will quickly go to tell you that a equals to 1, b equals to minus 2, and c is equal to 2. I think I showed you guys that a while ago. It may not seem much easier, but it actually is. Yeah, whatever. Anyway, have a good break. Oh, okay.